take a look at hypothesis testing and how these things work. Just a quick rundown. So the goal of a hypothesis test, we're going to assess evidence about some claim that's being made about a population. So here's an example. Somebody makes a claim like chickens lay 3 eggs a day. So maybe I don't think they're right. So I'll collect some data. So I randomly select 10 chickens and they averaged 4 eggs per day. Now, although this is higher than 3, it we can't necessarily say that the other person is wrong, because what we need to do is we would try to determine how likely I got my results if I was supposed to get 3. So in other words, what's the probability I got 4 eggs if the claim is true that chickens lay 3 per day? Um, if that's a high probability, then I fail to reject the claim. If it's very unlikely that I got 4 if I was supposed to get 3, then I will reject their 3. So let's say the probability of me getting 4 eggs per day, if I was supposed to get 3, is about 23%. So about 1 out of every 4 samples that I would do would get 4 eggs. That's not that unlikely. So that makes me think that finding or accepting this idea that chickens lay 3 eggs per day is true. So how this works for us in this class, the outline of a test, the first thing we want to do is set up a hypothesis. We're always going to use parameters. In other words, it's always going to be either mu or p for us in this class. Now, the null hypothesis always has some type of equality. In other words, like we've discussed before, equals less than or equal to, greater than or equal to, it has to have one of those symbols. Once we kind of set that thing up, then we figure out what type of test. So the types of tests, we could have a t-test, a z-test, or a one proportion z-test. Those are the 3 types of tests that we know right now that we'll be discussing in this particular unit. Then we'll go ahead and calculate a test statistic. Easiest way to consider a test statistic, it's going to be the observed value minus the predicted value over the standard deviation of the sample. Depending upon what the type of test it is, that could be sigma over, it could be sigma over the square root of n, it could be s over the square root of n, or it could be the square root of pq over n, depending upon what type of test we run. The next 2 parts of this, the next thing we want to do is we want to make a decision. We want to make a decision based on our p-value, which we'll take a look at how to get. And then from there, we're going to answer in context. I always want to keep the context of the problem in mind. So let's take a quick look at how to set some of these up. So in Illinois, random sample of 85 8th graders has a mean score of 282, standard deviation of 35 on this national math test. The test results, a state school administrator, well, he'll drop it a little bit and say, okay, I think our average is definitely more than 275. So what is a parameter of interest? That's right there in red. It's a mean. So translate any statements that we have. Mean is more than 275. In other words, mu is greater than 275. Well, what that tells us, the other option then is that mu could be less than or equal to 275, or that the average is 275. Both of those, a strange thing here, are actually kind of considered the opposite of greater than 275. So if we remember that equality always goes with null, then the null hypothesis here will be that mu is less than or equal to 275, while the alternative hypothesis is that mu is greater than 275. Try another one. Manufacture of a sprinkler system. We're talking about the average. So right away, if we talk about mu, is at least. So at least translates as greater than or equal to. That goes right there, 135. To test this, we randomly select those two. Here's our data. So if it's not greater than or equal to 135, it has to be less than 135. Nutritionist claims that the mean tuna consumption, here we go again, so the null, HO, mu, HA, mu, right? We're always going to be talking about a parameter. So the mean tuna consumption is 3.1 pounds per year. And then the alternative, is there evidence? So a random sample shows that the mean tuna consumption is this. Is there evidence to support their claim? So we don't know if it's supposed to be less than, greater than, so we'll just say if it's not equal to 3.1 pounds per year. Right? So trying to set some of these things up. So maybe we go through a full example. Home Depot brand light bulbs state that on the package they're going to last 1,000 hours. We think this is too high as a class, so we tested 60 random bulbs. We got this average life with a standard deviation of 120. Is there evidence to support or to reject Home Depot's claim? So first things first, let's set up some hypotheses. So the null hypothesis, this is an average problem, so we're talking about mu. They think that the average is 1,000 hours. However, we think the number is high, so we think that it's actually less than 1,000 hours. Right? Type of test determined by the parameter and the conditions. So right now, it's a mean test, so it's either Z or T. We need to take a look at this standard deviation we're given is actually S. We don't know sigma, so what we're going to have is a one sample mean t-test. We might also just call that a t-test. Right? Now, the conditions, one, was it random? That was stated. That was given to us. The next condition, that we have normal distribution or that our sample size is big enough. Here, and it's greater than 30. That's the one that we're after. So this one was given, and we had means that were big enough, so we're good to go. Calculating the test statistic. So for us, our average, if we'll go back real quick, was 970 with a standard deviation. So our observed value is 970. We were supposed to see an average of 1,000. There's 120 over the square root of 60. And what we should have realized, if we did that, that's negative 1.936. So, in other words, how likely is it that we are 1.936 standard deviations below the mean? Well, we know from just empirical rule and everything, that's not all that likely. But we need to make our decision based on the probability that we got our outcome. So, in other words, we need to figure out what's the probability that we are almost 2 full standard deviations below. So our p-value is that area right there from negative 1.96 standard deviations. So that probability for us, quick calculation, that probability turned out to be, 0.029. So what we want to look at is how likely is it that we got that. So a p-value, real quick, is a probability that we got our results or that we get something more extreme. So the smaller the p-value, the more evidence it is that we reject the null. A lot of times they're going to maybe give us a significance level. Note that that's what the alpha level is. But if we don't get it, we're going to use 0.05. So our example, again, 0.0288. So because 0.0288 is less than 0.05, we reject the null. Excuse me. So to interpret those results, if we rejected the null, then our evidence here, excuse me, our evidence suggests that the average life, so if we rejected the null, that means that we're going to, in favor of the alternative. And so for us, that means that evidence suggesting that the average life of the bulbs is less than 1,000 hours. We're not going to claim that we have a new life. We just know that our evidence suggests that theirs is wrong. We'll try what's called a two-tailed test. And basically, that's when we're going to involve not equals to. So let's look at this example. A manager for a company reports that they have an average of 150 sales per year. So right away, mu equals 150. His boss suspects that it's not accurate. So in other words, boss man thinks it is not 150. Right? And the reason, again, I'm using mu is because it's the average. So when we see that it is not accurate or not equal, this is what's going to end up being a two-tailed test. We're going to have to consider, well, maybe they're making more than 150 sales a day. Maybe they're making less. We're not sure. We just know the boss thinks that the 150 is not right. The boss isn't giving us an indication of more or less. The boss just says, hey, it's not right. So once we've got our hypotheses set up, let's go ahead and think about what type of test we would run. Since, again, what we have is a sample standard deviation, right? This right here, that is S. That means that we are about to run a t-test. So let's go ahead and run this t-test. So this is a t-test. What's going on with my pen here? A t-test. And since we know it's a t-test, go ahead and drop your degrees of freedom in here. Remember, that's n minus 1, so we have 34 degrees of freedom. Our test statistic will be t, and that's going to be our observed value of 143 minus we should have seen 150 sales, and then 15 over the square root of those 35 sales. That value is going to be negative 2.76. Real quick to make sure that we do this, that we're allowed to do what we're doing. Conditions, SRS, I'm pretty sure it didn't say that, so we're going to assume that that's the case. Good news, we don't care if it's normal because we have a big enough sample. So with that test statistic, one of the ways to look at this, how likely is it that we're either 2.76 standard deviations below or 2.76 standard deviations above, right? So on a standard curve, how likely is it that we're this far out? So our p-value is actually going to be these two areas added together. The calculator, luckily, kicks that value out for us very nicely. Our p-value here is 0.009. Well, if you'll recall, we were told to compare to an alpha level 0.01. So right away we can see 0.009 is slightly less than 0.01, which would lead us to reject the null. So what that tells us in the context of this problem is that evidence suggests that the average number of sales per day is not 150. It's important to realize, even though 143 is less than 150, because our hypothesis was originally not equal to, right, we just realized we just rejected this. So this is what we think is true. This is what we have to accept. So we can't go out on a limb and say, well, 143 is less than 150, so that's the new answer. No, this is it. That's all we can do with it.